In our previous lesson on hysteresis, we observed how systems remember their paths. When disturbed, they rarely return to baseline immediately. Instead, they trace asymmetrical loops, delaying their recovery before eventually settling back into a stable state. This brings us to the final question of this series. What happens when a system is disturbed and recovery is no longer possible? There is a strict boundary condition in general emergence mechanics. Every persistent structure, no matter how resilient, has a horizon. For a time, a structure can absorb a shock. It can bend, compensate, and reroute its internal flows to adapt to the pressure. But these adaptations require a constant, active expenditure of energy. Failure begins when persistence becomes too expensive. This inequality represents our foundational admissibility condition. Here, A cost represents the total energy and structural cost required to maintain a system's current configuration. A crit represents the critical cost, the absolute mathematical limit of that specific system's coherence capacity. As long as the total cost remains below the critical threshold, the system can successfully hold its identity against external pressures. The moment that cost meets or exceeds the critical capacity, the system loses its admissibility. It must change state, fragment, or die. To an outside observer, this final break often looks abrupt. A structure that has held for years suddenly shatters under a seemingly minor strain. But the loss of admissibility drains the system slowly over time. The structural integrity was spent long before the visible collapse. The last break is only the receipt. Every persistent system operates on a coherence budget. It possesses a strictly finite reserve of energy and structural integrity. This chart shows exactly what a system purchases with that budget to survive. It buys structure, flexibility, speed, memory, redundancy, and repair. In purely mechanical terms, failure is the point where payment can no longer be made. This exhaustion takes several distinct mechanical forms. The first is depth collapse. Depth is simply a system's reserve capacity, the margin that allows it to absorb a disturbance without losing its identity. When a system's basin is shallow, it lacks that protective margin. A minor perturbation that would normally be absorbed instantly knocks the system out of its operational boundaries. We see this in hospitals operating with 0 spare beds, or supply chains completely stripped of their buffers. Under calm conditions, they function perfectly. But a shallow system turns small shocks into large failures. The second mode is stiffness failure. A system requires stiffness to maintain its shape, but there is a mathematical limit to rigidity. When a structure lacks the ability to bend or adapt to external shear forces, it cannot dissipate the energy of a disturbance. It simply snaps. This is the physics behind rigid institutions that shatter under societal pressure, or inflexible belief systems collapsing when reality diverges from their models. Stiffness preserves identity, but excessive stiffness turns identity into brittleness. The third failure mode occurs when a system gets stuck. This is viscosity failure. In GEM terms, viscosity is delayed recovery, a state where a system is disturbed but cannot return to its original form. The structure is pliable enough to bend, but it utterly lacks the elasticity to bounce back. This physical freezing mirrors human chronic stress long after a danger has passed, or persistent market fear that lingers even when the triggering event fades. The system does not collapse because it failed to respond. It collapses because it could not stop responding. The fourth mode is routing failure. Here, the system still possesses its individual parts and sufficient energy, but internal flow is critically obstructed. The network remains fully powered, but as the pathways sever, it becomes structurally blind and disconnected. We see this in physical reality through broken supply chain links, blocked transport corridors, and decision-makers effectively isolated by institutional information silos. The pieces remain, but coherence between them is gone. The fifth mode is a slow fade, gradient failure. Gradients are the underlying differences in concentration, pressure, or energy that allow any system to perform work. Without these distinct contrasts separating a system from its environment, all internal processes simply stall out. This is the physics of a discharging battery. It is also the mechanics of a social system or a human mind losing its motivation, drive, and meaningful distinctions. In a gradient failure, the system may not explode. It may simply lose the capacity to do work. The final mode is coherence overload. This occurs when a system is forced to integrate vastly more complexity than its finite coherence budget allows. In overcoupled networks, hyperconnectivity doesn't lead to increased efficiency. It leads to cascading system failure. This is the mechanical reality of overwhelmed human minds, excessively complicated institutions, and modern environments completely saturated with unverified signal. There is a strict rule to systemic scaling. Complexity is not free. Every connection adds possible flow, but also possible friction. Overload happens when the cost of managing that friction bankrupts the system. But exhausting a coherence budget does not always equate to absolute destruction. A failure of one configuration often forces a transition into another. This state space diagram shows 3 distinct schematic paths a system faces when forced out of its current configuration. First, the system may successfully pay the high cost of recovery, looping back to its old basin. Second, the pressure of the crisis may loosen the old structure, allowing the system to drop into a newly formed adjacent basin. It transitions. Third, if the system lacks the depth and flexibility to transition, it shatters entirely, decohering beyond recovery into noise. This divergent branching explains why a crisis can be either creatively transformative or entirely destructive. The outcome depends strictly on the system's remaining depth and flexibility. Transformation is not guaranteed. It is admissibility under pressure. Throughout the series, we have mapped the building blocks of persistence. We started in the foundational physics of emergent constants, observing how chemical handedness creates bias without external forcing. We scaled upward into biological bounds, watching macromolecules fold without friction, mapping the exact physics of cells as gradient shields, and tracing the persistence architectures of complex networks. Through all of this, general emergence mechanics maintains a strict, unsentimental philosophy. GEM does not say everything can be saved. It does not even say every structure should persist. Systemic failure is not a moral punishment. There is no cosmic anger in a collapsing bridge or a dissolving cell. It is a purely mechanical outcome of exhaustion. Failure is the end of an admissibility claim. Every persistent structure must pay the cost of remaining coherent. The universe does not keep everything. It keeps what can hold. Which leaves us with one final question to ponder. When a system fails, has it ended, or has it crossed into a form that can no longer remain itself?